Continuing on physical chemistry, we're now beginning chapter 3 with section 1. In this chapter, we're going to talk about the second law of thermodynamics. Now remember, the first law of thermodynamics said that the change in internal energy was equal to Q plus W, with Q being heat, W being work. This is only true for a closed system. So we have the change in the internal energy of the system plus the change in internal energy of the surroundings is equal to 0 by the conservation of energy. The change in internal energy, delta US subscript SYS, that's change in internal energy of the system. And SURR is surroundings. This is subscript for the U. Now, based on the first law, there are no restrictions on energy transfer except for the conservation of energy. The second law says there is a state function entropy, which we will symbolize by capital S, that wants to increase. Now, Clausius was German. He was the founder of thermodynamics. The Clausius version of the statement of the second law says, "It is impossible to devise an engine which, working in a cycle, shall produce no effect other than the transfer of heat from a colder body to a hotter body." So here's what we're showing here. We have our system here. There's a cold reservoir and a hot reservoir. We don't need to know the temperatures, just to know that this is hotter than that. So remember, plus Q would mean going into the system. Minus Q means coming out of the system, right? We would expect energy to flow from the hot reservoir through the system to the cold reservoir. But that Clausius says that is impossible. So that's why if you want to take a cold reservoir and make it even colder, like what a refrigerator does, it actually takes energy to operate. You actually have to use energy to pump the heat that way. Now, another statement of the second law is the Kelvin-Plank statement. It is impossible in a cyclic process to convert heat into work with 100% efficiency. Now, violating this would be considered perpetual motion of the second kind. Perpetual motion of the first kind would be violating the first law of thermodynamics. So, let's say we have a heat reservoir in our cyclic machine, and somehow Q goes in, work comes out. We can abbreviate that W, of course. Although actually coming out, then I guess it would be minus W. So work output equals Q. That's impossible. This machine violates the second law of thermodynamics. Okay, that's all for section 1.